There we go. Like I said, Louise is recording this, so if you want anything, you can go back later. And we'll also be sending out to the mail list of everybody who RSVP'd. The keynote for tonight, we'll put it in PowerPoint format, and we'll send all those resources out to everybody when we're done also. So, well, let's get right started. Our warm-up is going to lead us right into our new activity. We are pretty excited. We've got some really new things out there for everybody to share and hopefully start using in your classroom. And we're going to actually do the warm up on one of these, which is a new ICE lab. And ICE stands for Ice and Climate Explorations. And these are a new series of labs that we're developing. There's two that are fairly well developed right now. We still call them in draft mode because we're field testing and we might tweak them a little bit. But there's two that are pretty much ready to go where you could take them and use them in your classrooms. And there's two or three more in the pipeline that are going to be coming soon. So we wanted to give you a little preview of these ICE labs. They're called Ice and Climate Explorations, and they consist of multiple explorations in each lab activity. And they scaffold the kids through increasingly complex concepts. So you can see the one that we're going to play around with tonight has 5 different explorations, mini explorations as part of that whole ICE lab. The other new thing that we've added is these drill deeper video shorts. So this is a combination of short little videos that we found out on the web that we think are really good resources, and then new little video shorts that we're developing along with the climate scientists like Sarah Shackleton, who you hear later tonight. She is actually going to be making 2 of the video shorts in the same mode that you're going to see. We'll show you one demonstration, one tonight that's done, but she has 2 coming, and we have other people in the pipeline as well. So these are opportunities for you to get the actual scientist into your classroom to talk to your kids at a really high level in about a 5 to 10 minute block. So it doesn't dominate your class, but it does hopefully enrich your class. So we'll show you both of those as the night goes on. So this first lab is about dating ice cores. And if you've been with us either in School of Ice or Train the Trainers, we usually start with a little warm-up activity where we try to date and count how many years of ice are in an ice core. We're going to start the same way tonight, except we're going to use a different ice core than you guys have seen before. This one is actually from Greenland. If you are new to us and have never done this before, I'll just give you a very Cliff Notes version of it. When you have an ice core, and this is actually an image of an ice core from Greenland, it's called the GISP-2 core. You'll see light layers, and those are a result from snowfall that falls during summertime. You'll see dark layers, and that's snowfall that fell in the wintertime. So if you have a pair of dark and light bands, one pair of light, one dark and one light, that's 1 year of climate science or climate record that's trapped in the ice. So I do want to decode some of the stuff at the top for you. If you look at the very top here, you'll notice that this is called the GISP-2D 1866 core. So that means this is Greenland Ice Sheet Project. The second one, and the depth, the D stands for depth, 1,866 meters down. So that is how deep that core was. Also, I want you to notice that here the age of the ice at 1866 at this end, the age of the ice is 17,336 years. As we were developing this, it kind of blew my mind. They said it was plus or minus 5%, which sounds like it's pretty good. I know if in my classroom, if my kids are within 5%, I'm like, that's really good data. Well, awesome, great. But plus or minus 5% of 17,000, that's 850 years. So one of the biggest challenges that ice core scientists have is getting dates as accurate as possible of the ice that they're looking at, because they can do all sorts of analysis of things that are in the ice. They can tell you the temperature, they can tell you what the climate was like, how dry it was, how many forest fires were burning on the planet. They can tell you an awful lot of things, but if they can't tell you the date, how old the ice is, it's kind of meaningless. So we're going to spend about a half hour together and really learn some different techniques and some more advanced dating techniques even than just counting. But we're going to start by counting and learning how to use the annotate button on your Zoom if you don't know how to use that. What I would like you to do is tell me the approximate age or the number of years of climate data that are in this image right here before you. And then once you get that, I would like you with this other information at the top to assign an age for this end of the ice core at 1865.5, your estimated age at that end. And I'd like you to actually use your annotate button. If you look on the bottom left-hand corner of your screen, there should be a little tool that says annotate. If you click on that, you'll get a menu item where you can actually annotate and choose the T for type and type in a number. That was a lot of instructions. How many years of climate data are in this picture? One band of light and one band of dark makes 1 year. Count it up yourself. Use the annotate button to put the years of climate data in this box. Then use this information at the top to assign an age of the ice in that box.
Where is the annotate button?
Annotate button is on the, should be a little pencil on the bottom left-hand corner of your screen. It's like a pencil over a line. And that brings up another menu where you can actually choose a little T to type.
Yeah, it's not actually on the very
pen.
bottom, but if you look in the left hand, yeah, it's there.
Somebody's marking it for us on there. I like this.
Yeah, mine's not letting me type, but I'm going with 30 years.
Okay.
Yeah, me too. I'm not able to type, so I don't know why I can't.
I'm only just able to kind of scribble.
Yeah, that's all I can do.
Scribbling is okay.
Okay.
All right. So I happen to know John Lewis fairly well. He's actually a big data guy. So John, I'm going to ask you to look at all the numbers that are in the years of climate data and just come up with a group consensus. It's an eyeball average or median, whatever you want to put in there. And then I'd also like you to give us a plus or minus how many years you think from this group that just did that analysis, how much slack we should give ourselves plus or minus once we put an actual number on it like they do in the top ice core. So while John's coming up with that number for us, I'd like to point out a couple things. First of all, the range of numbers here is pretty big, from 120 down to 7, I think, or something like that. So I love activities like this where people just can come up with their own data, their own numbers, because now if I'm doing this in class, there's a really good reason to have a rich discussion about this data and have people start to explain how they got 17, how they got 25, how they got 48, how they got 120, and evaluate each other's answers. That I think they call that science. So the other thing that I want you to notice is this takes that activity that a lot of you have done where we just count the layers to a whole nother level, because now if I'm asking you to estimate the age of the ice at this, you have to do a couple things. So John's come up with a number for us that there's 25 years of data here, just group average. We'll take his number and believe him, plus or minus 10 years. So we have in 25 years, we're plus or minus 10 years according to John. So that means that we're what, 40% plus or minus 40% in just 25 years of data. So now if you look at their 17,000 years of data and they're at plus or minus 5%, all of a sudden that number starts to look a little bit more impressive. Yeah, to go down 17,000 and only be 5% off, or plus or minus 850 years. So let's come up with a number over here, an estimated age. If we use this group consensus number of 25, and our age over here is 17,336, this is 1,866 meters down. This is 865.5. So that would be 25 years less, because it's towards the top. It's not as old. So John, as long as you're typing here, could you put in there 25 minus that would be 17,311? If my mental math under pressure here is right. 17,311 years. And then we added plus or minus 10. So now we would have to say we're 17,311 years plus or minus 860 years. So we've just added 10 years to their plus or minus. So I think right there you can see that any questions or any comments on that? I think you can see right there, we've taken what was a simple activity, just count the years of climate data. It still starts out the same, count the years of climate data, but all of a sudden we're learning a lot more about ice cores, about uncertainty in their measurements, about the top of the core versus the bottom. And if we're going to go up or down, that's always a really important thing, is to say, hey, which side is the top of the core? One of the first things they do is mark the top, and they keep the top all the time so that they don't get that mixed up. So let's see how we can even get better than this. Don, go ahead. Question, yeah.
Yeah, I just, I had a difficult time in some cases saying what was dark and what was light. I mean, I think maybe if I had the actual ice core or whatever, might have been able to do a little better.
So you're saying that you want some more, maybe some enhanced ways to see those layers than you're looking at right now.
Sure, that would be a good way of putting it, yeah.
Thank you, Don. With that, let's go on to the second exploration. And let me see if I can clear my annotations here. Erase, clear all drawings. All right. So here's the same ice core analysis, the same ice core that you were looking at before, the GIST-2 core, 1866 to 1865. But this time they took a little chunk of that ice all along the way and they melted it, and they measured the dust particles in it. They do what's called laser dust analysis on the ice core. And what you get is a trace that looks like this faint green one in there that shows how much dust is actually trapped in the ice at each different time period. And the little hint here is that in Greenland, the amount of dust in the air that consequently gets trapped in the ice tends to peak every spring. Every spring there's a peak of dust and then it goes away. So let's do the same game on this one using the dust data. Could you estimate the number of years of climate data? I gotta stop sharing here and close. Could you estimate the years of climate data in this ice core now that you have that expanded? And these are 0.8 to 10 micron dust particles. They actually do this analysis for all different size dust particles than just this one, but that's fantastic. And I'm going to ask John, my data expert, once again to come up with a group consensus number and a plus or minus now that we have laser dust to look at, as well as the visible layers that we were counting before. And John would say you can give me a verbal also, John, if you want. 16 plus or minus 2. Look at that. Look at how our precision has improved. With more information, we can start to narrow that band of plus or minus down and get the number a little bit more and more precise. Excellent. Once again, now that we have that, we could add it on and we could do the other side as well and estimate the age at 1865, but I think you get the idea behind that. Don, does that help? Is that what you were looking for? Or Don, would you like even a better way, more accurate way to get specific ages?
Hey, I got a quick question while you're on this slide.
Yes.
So when I first looked at this, I was wondering, is there something misaligned? Because like the peaks are they supposed to be on the darker pieces?
That's a great question. I looked at that also because, we're getting data from 1,800 meters down, and if you just shift things one way or another, the scientist who gave this to me, he was pretty adamant that this is an overlap of that section, and I actually thought the same thing. Like, shouldn't that be shifted and like lined up with the dark? But then when you realize that it's peaks every springtime, and if the dark layers are winter layers, springtime would be just after the dark layers.
So it's not necessarily supposed to line up with the dark layers.
No, because the dust tends to peak in springtime.
Right. Is that and that's my other question. Is that explained somewhere in this exploration somewhere else?
Yes. Yes,
okay.
Without a doubt.
Okay, because I looked it up just to see, well, what's the case there? But
you mean explain why?
Yeah, why dust is peaked during springtime
at that time of the year? No, but that might be a good thing for a drill deeper video.
Yeah.
So we might add another drill deeper video where somebody explains why the dust peaks at that time.
Yeah.
Yeah, that would be good. All right. Let me clear this annotation away and we'll show Don some more data because he's not happy with that yet.
I was actually pretty happy with it.
Come on, Don, you're setting me up here. How about volcanic data? So, ice scientists love volcanoes because when they erupt in a huge volcanic eruption, they leave a layer of dust, which is almost like an index fossil. If you're a paleontologist, it's an index layer where they can get back on and they know exactly how old that is. So, here's the GIFS 2 core again, the same exact core from Greenland. This is 481 to 481.06 to 481.16. That's where they took this micrograph. And that micrograph shows a whole bunch of these little pieces, which are actually volcanic tephra or ash that's been blasted out of a huge volcano. Now, remember, when they were looking at that, we were plus or minus 850 years at that depth, or at 1600. I'm not sure what the plus or minus is at 481, but it's definitely a big number. So there's 3 different known eruptions, furnace that happened at 35 CE, which is common era. That's like after year 0, 35 CE is common era. Okmak volcano, which is 43 before the common era, that's BCE, or Mount Etna erupted at 44 BCE. So what the geologists / ice scientists will do is each one of these volcanic eruptions has a very unique fingerprint of the chemistry of the ash. So when we look at on the right side here, we see these multicolored graphs. Let me explain what each one is. The top graph is aluminum oxide versus silicon dioxide. Those two plotted against each other, and here are the ratios of the chemistry of this ash has these ratios of silicon dioxide to aluminum oxide. These are the ratios of silicon dioxide to magnesium oxide. These are the ratios of silicon dioxide to potassium oxide. So you can see that each one of these eruptions here at the top, Etna is this light green color. All the ash from Mount Etna, they know has that chemistry. All the ash from Okmok will fall in this purple one. All the ash from Furnace will fall in this one. So now it's just a matter of your students graphing these data and seeing which one of the volcanoes is responsible for this ash layer. So if we plot the silicon dioxide or silicon dioxide and the aluminum oxide, that's where the data points end up. Can we learn anything from that?
I would say this was a BCE ice core, not a CE ice core.
There you go. So you're going to eliminate Furnace because none of them actually fall on Furnace. And I would say the same thing. So we're starting to say, okay, Furnace is out. None of the chemistry lines up with that. I'm not sure about these two because we got 2 in this one. We got 1, 2, 3 in this one overlap. So let's look at another chemistry or chemical fingerprint. Let's look at the magnesium. If we look at the magnesium data, it plots there.
Yeah.
It's right smack dab in both of them. So that doesn't help us out. So let's look at the potassium data. If we look at the potassium data, it plots there.
Yeah.
Now you can say, okay, we got a match. I think we know that this ash layer is from Okmok, a very well-known volcano, and that ash layer is 43 BCE, plus or minus nothing. That is it. We're back on track. So as they're going down the cores, they tend to drift more and more and more in their precision. But then if they can get an ash layer, boom, they can lock it back in. And all of a sudden, you're not plus or minus 5%. You're back to 0. So let's look at how this combines with other ways that they can analyze the ice. The fourth exploration in this new lab is about sea ice aerosol. And there's some facts about sea ice aerosols. This is usually from shallower layers. It's called destructive ice core testing because they have to melt some of the ice that they bring back. So once they melt it and do this test, that's gone. That ice core is done, or that piece of the ice core is done. And in this case, winter storms tend to make the sodium levels from the sea mist peak in the wintertime. So there is sea salt data for an ice core, along with our ash layer that we know is exactly 43 before the Common Era. So in this exploration, we'd be asking to say, hey, could you or your students calculate the age of the ice at 388 meters? And again, each one of these peaks is going to be a peak in the wintertime. And we could play the same game, except now we're not plus or minus 850. We're plus or minus just whatever it is that we would have a trouble estimating over here. And we could play that game. You could all put that down and we could get there as well. Teacher to teacher, when I was talking with the scientist who gave me this data, one of the questions I had was, well, I get confused when I'm in a zone like this, where there's like 3 little peaks. Is this like 3 years of data or is that 1 year of data? I'm not sure what's going on there. He didn't give me an answer, but he gave me guidance. So I guess that's okay. Here was the guidance he gave me. He said, what we do is try to look at the average space between them. And if there's a question, we always just fall back to take the average spacing and keep it simple. Keep it with the average spacing. And that's how we would take our best guess at it. So that's the fourth exploration. But remember, this New Ice Lab has 5 because Don's not just happy with 4. He wants 5. He wants more. Don, you got a question?
Yeah. So yeah, we need back to, I don't know who asked the question before, but you know why is it higher sodium? Obviously, there could be some little seasonal strange seasonal thing that happened, and these years here at between say 389.5 and three. There's this one big peak, two little peaks, and so something could happen for whatever reason. The sodium is higher, so it
Yeah,
looks to
so
me anyway that the tall peaks are the ones that we should think about. Not
every
the
tall peak, again, when there's a lot of wave action, you get a lot of sea mist, and that puts all the
Okay.
sea mist aerosol up in the air. That's where the sodium's coming from. And the storms tend to be a lot more violent in the wintertime than the summertime.
So you could get
That's
an
why
occasional
yeah, you'd
summer
expect,
storm. That's yeah. Okay. Yeah.
so every peak is a winter, every
Yeah.
trough is a summer.
And these little side things are just okay. We had a little storm when it wasn't supposed to happen or whatever.
Something like that, yeah.
Okay.
All right. So let's look at one more technique that is used to date ice cores and try and narrow that down. This is called ECM data, electrical conductivity measurements. And the nice thing about ECM data is that it's non-destructive. They can run this test on the ice core without melting it, without destroying it. It's one of the first things they do when the ice core comes in. They image it, they take pictures of it, and then they run ECM data on it and just to see what it shows, basically. So here's how they do the actual experiment. They take two electrodes 10 centimeters apart, and they just run 100,000 volt potential between it, and they just run it down the entire length of the ice core. And they move over, do it again. They move over, do it again. So when you look at this rainbow on the screen, each one of those is a different track. And this is the actual machine that they do it with. And I think this will help. There's the two little electrodes, and they're just being dragged down the ice core, measuring the potential between the ice. Then it zips back and they move over a little bit and they do it again. So they do this with every single ice core and they have this data. So what we've put together for your students is a couple different ways or options for you as a teacher, depending upon what level students you're working with and how deep you want to go into this. But we've put a couple options together. One is to just hand them this graph. This is all of the different tracks, 7 different tracks plotted, the conductivity plotted as we move. And I'm going to just double check here. This is the top of the ice core on this side. This is the bottom of the ice core on this side. It's reversed because it's plotted with Excel spreadsheet, which has a hard time going in reverse order. So you can see again, we see this type of seasonal variation. Every time it goes up in a peak, that's probably one season, and then down and another season, and because this one is from fairly shallow in the ice core. So when it is shallow like this, the conductivity differences do tend to indicate differences in seasonality. So the different options we have for your kids are you can hand them this graph where it's already plotted. They could estimate the age. Or we have a link in the lab to the actual raw data. So if you want your kids to take the raw data and generate their own Excel spreadsheets, all of the raw data from this chunk of ice are there. We've had a lot of people over the years ask us, hey, can I get a hold of raw data and can my kids work with the actual data that the scientists are getting? The spreadsheet is there for you. It's a lot of data. They go every, whatever that is, they're 350 point centimeters, millimeters, all the way down to whatever less than a millimeter is. There's a lot of data. So another option is color coding just a smaller section of it. So we cut it down to 25 centimeters. We eliminated some of the data. And so your students could go in on an Excel spreadsheet and just use the paint tool and paint the different layers. And you start to see these patterns come out in the ice. Or we've actually provided the actual sheet where if it's a snow day and they need something to do at home, you can give it to them and they can get colored pencils and color it by hand. And just have a color day where they're coloring and it ends up to be the same way as the paint buckets. So 5 different options, or actually 6 different options to look at that ECM data from you. And then when you're done with that ECM data, the real question is, well, what does it mean when it's not just shallow like that, where you're counting annual layers, but what about if you have ice that's like 6 million years old, like Coldex is looking at? Because when the ice is 6 million years old, there's none of these layers, annual layers visible anymore. Is there still a difference in electrical conductivity? So to show you with that, what we'd like to do is if you look at these ice, the drill deeper ice videos, the drill deeper videos, we have Liam Kirkpatrick, who works at the University of Washington, put our first drill deeper video together. And I'd like to just show you that video so you can see what it looks like. Notice that there's some linked up here after exploration 1, 2. There's already some of those that are done just of the ice core facility where you can watch those videos. Here's Liam's that we're going to take a look at. And Sarah Shackleton, who you're going to hear from very soon, she's going to have her own, going over a lot of what she's going to talk about tonight that you can go back and use with your students later. But let's take a look at Liam's and you'll see what these are like. And I'm going to stop sharing for a second. I'm going to reshare because I don't know if I shared sound for you.
Hi everyone, my name is Liam Kirkpatrick. I'm a graduate student at the University of Washington. Today I'm excited to chat to you about my current project, which is looking at 3-dimensional layering with electrical conductivity measurements, or ECM, in the hunt for oldest ice. This project is funded by the Center for Oldest Ice Exploration, or Coldex, which is a science and technology center funded by the National Science Foundation. I'm also really reliant to the National Ice Core facility funded by the National Science Foundation. So this project is taking place at this spot in Antarctica called the Allan Hills. I've showed kind of roughly where it is with this red box on the map of Antarctica. And then I've zoomed in and showed the location of 2 cores, Allan Hills Ice Core, ALHIC 2302 and 2201. So these are 2 cores that I've looked at, and I'll show some data from in this plot. As you can see, this is a really bizarre spot where you can see that blue tinge in the satellite imagery there. And that's because this is a spot that's so windy that we're actually kind of wearing away the snow and getting down to the bare blue ice that's coming up from deep inside the glacier. So we're finding really, really old ice at the Allan Hills. Here I just picked out 2 news headlines that show this. We're up to about 6 million years old. Which is way, way older than the oldest ice core before this project, which was only 800,000 years old. However, unlike a normal ice core, we're also learning that this old ice has been folded in this spot. So we're not going somewhere where we drill down and it just gets deeper the older, it gets older the deeper we go. Instead, we're somewhere where the layering has been folded up. And here I asked ChatGPT to illustrate that with a breakfast pastry for us. So you can imagine this adds some complications. We need to figure out the ordering of the ages and how the layer structures interact with the proxies like CO2 or temperature that we're trying to measure. And so if you imagine we drill our ice core through this cinnamon roll or through the glacier, and that's really all we can see. So we can only see that layering. But we can learn a lot about the overall folding just from this little snapshot. And so that's what we're going to be trying to do today. So to do this, we're applying electrical conductivity measurements in 3 dimensions to understand layering and folding. What does this look like? Well, I've got a little video going on the right of this machine just scanning back and forth. And sometimes I have to reach in with my hand and jiggle the electrodes to make sure they press in on the ice. But basically what we're doing is taking a pair of electrodes and we're pressing them onto the surface of an ice core. And we apply a constant voltage and we look how much current flows between them. Which changes based on the acidity and the ion content of the ice. And so on the left here, you can see we've got an ice core that we've cut into quarters. And here we've got 2 of those quarters, and we're going to scan perpendicular faces on those quarters to build ourselves a 3-dimensional map of the conductivity, and so of the layering in the ice. What does that look like? Well, here's some of the first images I made applying this technique. And so we can see really clear layering here. This layer in blue, which is a layer of higher conductivity, really pops out. And we've got this layer in red, which is much lower conductivity. You'll note this layer isn't flat though, it's dipping. This layer actually dips at about 45 degrees. And so this has some really big implications for us. One is that we can use this to study how layering changes over a long section of the core. So this is kind of what I talked about earlier, going all the way through our cinnamon roll. And so we can watch here, we've got our quarter core, and we've done multiple segments back to back. So the white gaps are the chunks between the segments that I can't measure. And we're going from 24 meters deep in an ice core and scrolling down. So right now we're at 29 meters, 30 meters. And so you'll see in some of these, the layering isn't really clear, but in other sections, the layering really pops out, like this one here. You'll also see the layering isn't flat. It's actually really steeply dipping. Here it's about 70 degrees. So that's, if 0 is flat, 70 degrees is pretty steep. But we see that it's consistent over this entire stretch of ice, which really helps inform how we sample the ice and how we interpret the climate records that we're building. I really like this section as well. Really clear, strong layering that really pops out at you. All right, we'll keep on going. We can also use this 3D electrical conductivity measurements to zoom in on really fine scale layering. So this is a figure I showed a little earlier. And the question I want us to think about here is, let's say you're a scientist and you're trying to figure out the relationship between CO2 and Earth's temperature. And so you might cut one chunk of ice and measure a temperature proxy to reconstruct Earth's temperature, and another chunk to measure the CO2 content. But you want to make sure they come from the same layer, so they come from the same time period. And you can see that's not really easy to do, because this layering is invisible to the naked eye. And so we've been working on methods that we can use these electrical conductivity measurements to inform how we cut our samples, so we can coordinate and build this kind of comprehensive picture of what was going on in Earth's climate. So here we've got a slightly complicated figure, so we'll walk through it. On the y-axis, so the up and down, we've got the depth in the ice core. And so we're at 155 meters down to 155.4 meters. So this is only a 40 centimeter chunk of ice. On the left, we've got our electrical conductivity measurements. So we're kind of looking top down at a section, and then across that is just the distance across the ice core. And then the boxes represent 3 different sets of samples in brown, orange, and purple that we cut from this ice. And so with that, we measured the water isotope content, or the delta 18O. And this is a proxy for the temperature when the snow that formed that ice first fell. And so on the right, I've just kind of thrown in a nice help for us. Colder is to the left and warmer is to the right for these 3 different sets of measurements. And so there's a data point on the right plot for every box on the left plot. And you can see when we first look at this, these 3 sets of data look nothing like each other, even though they're the exact same proxy measured on the exact same piece of ice. And that's because the layering isn't flat. But the good news is we can rotate our layering to go from tilted to flat, which will then hopefully line up our samples. And so we can test that like this. So now we're going to rotate our layer until the same layer is at the same depth all the way across the core. And you see as we do that, the water isotope signal on the right-hand side also lines up really well. This also tells us that in the middle of that layer, we have ice that's just a little bit colder, or was a little colder when it formed than the rest of the ice core section. So we hope this new 3D electrical conductivity measurement tool might help us unlock even better records from this really old ice. Thanks for watching.
Okay. Did you have anything else you wanted to say, Bill?
I do not.
Okay. It's my great honor to introduce our speaker tonight. So, Bill, if you'll take your screen off, Sarah can get set up. Our speaker tonight is Sarah Shackleton. She did her postdoc at Princeton and is now an assistant scientist at Woods Hole Oceanographic Institute on Cape Cod in Massachusetts. I recently found out that she and I have several common interests, including a love for animals. She has a cat and a dog, and I have a dog. We both love the ocean, and love to go shell fishing for clams and oysters, and we both hope to go scalloping in the near future. So I enjoy sharing that with her. Most of you probably also recognize her last name and are curious. And yes, she's a distant cousin of Ernest. So those of you that don't know the story of Ernest Shackleton and the Endurance, look it up. It's a great story. Sarah's working on how Earth's climate system has changed over time by searching for and studying the oldest ice on Earth. Most of you know that currently ice cores provide a continuous 800,000-year record of direct measurements of carbon dioxide and proxy measurements of temperature. At AGU, and I believe it was this past year, but Sarah can correct me if I'm wrong about this, but she talked about this discovery of a blue ice sample from Allen Hills that Liam just talked about, but she had also talked about a 4 million year old ice sample. She's going to talk about her research tonight, reconstructing global ocean temperatures and the dating of this super old ice. So Sarah, thank you so much for being with us tonight. We really appreciate it.
Yeah, thanks so much for having me. I had to quickly update Zoom and I was running a little late, so I'm really hoping that the web version is gonna work here. So I'm gonna try to share my screen in this presentation. Can people see my screen right now?
Yes.
Mm-hmm.
Yes, okay, great. Now we'll see if we can actually get into slideshow. Does that look okay to people?
Yes.
Yep, looks great.
Okay, great. Okay, so yeah, my name is Sarah Shackleton. I really appreciate the opportunity to be able to share some of my work and my research. And I'm going to be talking to you about a few subjects that have a common set of themes. One is that they utilize the measurements of noble gases in ice cores to learn something about these samples. And the second is that I'm going to be talking about these really interesting ice core samples from the Allen Hills. So the same kind of set of ice core samples that Liam had discussed. So we'll get started, and I think feel free to interrupt me with any questions. Okay, so we previously talked about different measurements in ice cores, but most of them have been about kind of the chemistry of the ice. So kind of sea salt concentrations, dust concentrations, water isotopic compositions. But for me, what makes me excited and what I like to study is the atmospheric gases that are trapped in ancient ice samples. So if you look at this photo here that my colleague Jacob Morgan took of a thin section of an ice core, what is quite beautiful and amazing about this is just these tiny little bubbles. So about 10% of the volume of glacial ice is actually air. And these little air bubbles are direct samples of the past atmosphere. So this is kind of one of the things that make ice core samples so valuable. Because of this, we've been able to precisely reconstruct past greenhouse gas concentrations going back 800,000 years. But in addition to greenhouse gases, we're also able to measure other types of gases that are in the atmosphere. And what I'll be talking about today is these inert or non-reactive gases, noble gases. And I'll be talking about argon and the kind of how we can use it to date ice cores when other strategies fail. And I will also be talking about how we can learn about how ocean temperatures have changed in the past using measurements of xenon and krypton in these air bubbles in the ice. And so we'll start with just how do we use argon to date ice cores. So what I'm showing here is this kind of very idealized, simple schematic of an ice sheet. And what the arrows show is kind of the flow of the ice over time. And as an ice core scientist, traditionally, what we do to select a site is we go to these areas called ice domes or divides. And the reason for this is because the ice flow is one-dimensional. So ice, basically, as it accumulates, it only moves downwards rather than outwards. And because of that, we get these kind of clean vertical layers of ice, and the ice increases in age with depth. And so kind of as we kind of had discussed, if you kind of look at these ice cores sections, you can measure things like dust concentrations or look at visible layers and count these individual layers to date an ice core. If you go deeper into the ice core, these ice layers get really thinned. So if you go deep enough, it's impossible to really count these individual layers with depth. But because we're at these sites where the kind of the ice flow is idealized, we can use glaciological models of the snow accumulation over time and how the ice sheet thins over time to predict how the age of the ice will increase with depth. There are also places near the ice sheet margins where you have old ice that was previously buried in the interior of the ice sheet resurfacing. And so that ice has kind of traveled tens of kilometers from where it was initially deposited to where it resurfaces, which allows us kind of an opportunity to get really old ice at or near the surface, but it also presents some challenges. So just kind of zooming in here, where kind of near the ice margin, we have these areas where the removal of snow and ice exceeds the rate of it accumulating. And so as Liam described, you have the exposure of glacial ice at the surface. And these areas are called blue ice areas. And kind of in an ideal world, in an idealized world, the further you walk towards the margin of the ice sheet, the older the ice should be. But in reality, because it's kind of undergone this complex flow, it can be highly thinned and highly folded. And that means that these assumptions that we made in order to provide constraints on the age of the ice at an ice dome no longer apply. And so we have to use alternative methods. And so the main method that we've been using at the Allen Hills, and one of the ones that I have focused on during my postdoc work, and I'll be focusing on as a researcher at Woods Hole, is this argon 40 atmospheric concentrations dating technique. And so the way that this works is that we have potassium is an element that exists in the crust and mantle. And one of the isotopes of potassium, potassium 40, is radioactive. And it radioactively decays into argon 40. So this argon 40 kind of remains in the rock and mantle until processes like weathering and erosion and magmatic degassing release it. And once the argon 40 is released, it stays in the atmosphere and it continuously accumulates with time. And so a really smart ice core scientist named Michael Bender had this idea saying kind of, can we use ice cores to understand the rate of this argon 40 increase in the atmosphere with time? And so we know the amount of argon 40 in the atmosphere today. He took well-dated ice cores and measured their concentrations in these samples. And with this, he and his colleagues were able to align to the data and kind of constrain the rate of argon 40 increase in the atmosphere over the last 800,000 years. So this gives us some useful geological information, but what's quite powerful for us is that it's also allows us to date ice samples of kind of unknown ages. So if you have an unknown ice, a sample of unknown age, you can measure the argon-40 concentration and then effectively place it on an age scale based on its its depletion relative to today. And what's really valuable about this technique is that you can date ice samples that extend beyond the continuous ice core records that exist today. So if you measure a sample that is significantly depleted in argon-40 relative to today, we can actually extrapolate that rate of argon-40 increase back beyond what has been measured, and we can use that to date much older ice. And so Liam kind of discussed this, but this is kind of one of the most interesting applications that we've used argon-40 for dating is at the Allen Hills in a project associated with the NSF Center for Oldest Ice Exploration, and basically measured samples from this site. And so I'll just show you kind of two of the cores that we've measured and kind of how the ice age has changed with depth based on this argon-40 chronometer. And what we see is basically that we have kind of this complex age versus depth relationship in both of these cores. And this is particularly well shown from this second core, this Alhick 1901 core, where you have these really complex age reversals. But what's quite kind of exciting and notable is that we've really significantly extended ice core records using these samples. So just to give you some sense, this is how far back the oldest continuous ice core goes. This is how old we hope kind of international projects will extend for continuous records. Previous work has dated ice back to 2.7 million years at the site, and now we have ice going back to about 6 million years. And so we can measure water isotopes on the exact same samples as we measure these argon concentrations. And so we can kind of produce these records of the change in the temperature at the site versus time. You can see this really nice record of showing this Antarctic cooling over the past 6 million years. But what else can we learn from these notable gas records? As we said, argon can help us date it, but we can measure xenon and krypton to give us temperature information about the evolution of ocean temperature in the past. And so the way that this works is that all gases, the solubility of all gases as water, the temperature of water decreases, increases. So colder water can hold more gases. And scientists have basically measured the temperature-dependent solubilities of different gases, including that of xenon and krypton. So xenon has a higher solubility in seawater compared to krypton, and it has a stronger temperature dependence in that solubility. But of course, we're not talking about samples of seawater. We're talking about past atmospheric samples of xenon and krypton. So how does this work? Well, together we can consider the ocean and the atmosphere a closed system with respect to these two gases. What that means is that the total amount of xenon and krypton together between the ocean and the atmosphere doesn't change. And so what controls the amount of xenon and krypton in the atmosphere is basically how much is stored in the ocean. And so if we increase the amount of heat going into the ocean, we increase its temperature. And what that does is it reduces the solubility of both of these gases in the ocean and leads to a net degassing of the ocean and an increase of xenon and krypton in the atmosphere. But because xenon's temperature-dependent solubility is stronger than that of krypton, you have a larger flux of xenon from the ocean into the atmosphere, and that changes the atmospheric xenon to krypton ratio. So just kind of to sum up what that means, if you warm the whole ocean, you increase the atmospheric xenon to krypton ratio. And so this is a really valuable proxy because it gives us constraints not on kind of local temperature, which is what the water isotopes that we can measure in ice cores tell us, but this gives us a global information about how the ocean has warmed and cooled. And so I just want to quickly show you kind of some of the records that we've produced from the Allen Hills from these noble gases. So, right, we get the ages of these samples from argon isotopes or argon-40, and then we get the ocean temperature evolution from this xenon to krypton ratio, and we can compare that to the record of Antarctic temperature change over the same interval from water isotopes. And so here are some records going back over the past 3 million years. These different intervals that are colored in different colors are kind of these different climate intervals where we've seen kind of changes in the cooling and kind of pacing of glacial cycles. But what's kind of exciting to see, and we expected it, is we see kind of these very similar trends between how ocean temperature evolved through these intervals and how Antarctic temperature evolved. So with that, I think I will stop here. And yeah, thanks for giving me the opportunity to present.
Thanks, Sarah. That was awesome. I think what we'll do because of time is go ahead and move on to our next speaker. And then if we have time at the end, Sarah, will you be here at the end so they can ask?
Sure.
Thank you. To introduce a participant who is going to share what he has been doing with some of the materials. John Edwards is also a scientist, and his participation in School of Ice has actually been sharing his work in the Coldex Gas Lab. He's also been a great help to us developing teaching resources, and you can see him in the virtual field lab titled Comparing Climate Change Past and Present, where he uses several different measures to compare climate changes in the Earth's past to the changes in climate we're experiencing today. This year, John has changed his career direction and is teaching science at Cascade High School in Turner, Oregon. He has a huge teaching load in a small rural school district where he's added oceanography, atmosphere, and climate content, as well as teaching physics and chemistry. His students, I know, are really fortunate to have him. I've seen him teach, and a lot of you have been at School of Ice in Oregon and have worked with him too. So we're really lucky that he's agreed to be here tonight to share his experiences with IDP resources. So John, welcome.
Hey, thanks, Louise. Good to see everybody. So I just wanted to share a couple of things. Let me make sure I am sharing the right thing here. Yep, and everybody can see that. Great. And so I just want to share a few of the ways that I have used the Coldex labs. I've used most of them except for the new ones. I plan on getting into those shortly. And I've used from Karen and Richard Alley, the Thwaites Glacier, and understanding how sea level changes and the kind of the fit and starts, how ice shelves extend and we lose ice in fits. We've done the CO2 labs, the water density labs, we've done the Alaskan labs as well, the virtual field labs. And so one of the things I really like to do when I'm teaching in my own class is I use it kind of as bookends. So we'll do a whole unit on atmospheric circulation and trying to link how that connects to our oceans and how CO2 is going into and out of the oceans in the biological pump. And then we get to see that with the data. We get to see that with the ice core data looking at our CO2 analysis lab. And students really get to actually do the analysis of the CO2, comparing how the rates changed in the past and how they are changing today. So they really get a very real world insight into what is going on and that our system today is fundamentally different than what has been in the past. So that's one of the ways that we have been using them. So you can see the atmospheric circulation there, and we can see that to the left there, that if we make any shifts to the atmospheric circulation, we can change wind patterns over around Antarctica, which can change how much CO2 is either going into our oceans or coming back out, which is fantastic for students to be able to see. Another thing that we also do is we spend a lot of time just on how changes in the amount of ice that's going into our melting into our oceans has impacted in the past and will continue to impact today how ocean circulation and our Atlantic meridional overturning circulation acts and responds. That's something that is in the news fairly regularly today, so it's a good one to add. And so this figure is actually a figure from Oregon State University. It's from Caden Martin, a press release from one of his papers on something called Heinrich events, where we had these massive discharges of ice into the North Atlantic, and this had really large impacts globally. Antarctica got a little bit warmer. We saw these really drastic decreases in the Asian monsoons. We were talking about dust earlier, so we saw a really large as Asia became much drier. We saw a lot of dust in Greenland. So in our ice cores, we see that. And at the same time, we started to see increase in monsoons over South America. And over to the right here, we can actually really analyze, and I do show them this data and have them analyze data and look and say what things are happening at the same time, right, as these Heinrich events are occurring. So they're able to really see the effect of having a large amount of ice going into the North Atlantic. One of the things that I learned from School of Ice is these little fun little water density experiments, which always blow students away. They always get it wrong. And it's something we all get wrong because we have all this formative knowledge and this foundational knowledge on how we keep ice off the roads. To melt the ice, we throw salt on it. And then we create a saltwater column and a freshwater column. We put an ice cube at the top and ask students which one is going to melt first. And surprisingly, that salt water will form a really clear freshwater cap on top, and the ice just won't melt. And we see the same thing when we had these big excursions of ice into the North Atlantic, that we'd create this buoyant cap on the top, and it would really disrupt our meridional overturning circulation. So students really get to see from that in a very real world example that the how salty the salinity of our waters affect ocean circulation. So that's a really fun one to do that we kind of finish off our ocean circulation unit with. And then the other one that I also really like to incorporate is, because we're talking about these glacial and interglacial cycles and understanding how the Laurentide ice sheet has waxed and waned over these cycles, it can be a little bit confusing for students as to why summertime temperatures are what's really the most important, because they're thinking, well, it snows in the winter. Isn't that when ice sheets would grow? But what the Alaskan Virtual Field Lab shows is that even if you get more snow in the winter, it's the summer can really fluctuate a lot, and that we can see it's important to both look at what's happening in the winter and in the summer, and that you can really see a dynamic change in how much snow actually melts in the summer because of the summertime temperatures. And so as a result, when we look at the Laurentide ice sheet, we see the same thing, that it's the summertime temperatures that really drives these glacial interglacial cycles. So I have found that every single one of the virtual field labs really works as a really nice kind of bookend to a unit to really draw everything together. And so we're going to continue. I taught the oceanography and meteorology classes last year, and we're going to be teaching them again in the next trimester and continuing to add more of these courses to them. So I'm going to leave it there. I know we are short on time.
Hey, John, I really want to thank you for that. And there's another virtual field lab in production right now about Earth's energy system and feedback loops, which is looking at how much ice is over the North Pole area and how many melt ponds are on Greenland and how much black carbon is landing on Greenland. So should be out this year sometime. I don't know if it'll be out for the spring, but it's close. And then we have another one that's looking at atmospheric chemistry, where you can actually see the results in the ice of things like the Clean Air Act. And you can see different atmospheric chemistry change based on political choices that we've made in the past, which I think offers some hope for the future. So those are two more virtual field labs that are coming also.
That's going to be fantastic. We'll be able to build a whole course just around School of Ice.
And all of us here are going to want your syllabus. Thanks, John.
Thank you.
And I want to introduce our next speaker. So, Keely, if you want to pull up your slides. Our next speaker is Dr. Keely Corder. Keely is the new Director of Education for the NSF Coldex Science and Technology Center. Coldex, you've been hearing from Sarah and also from Liam and John. Coldex is the Center for Oldest Ice Exploration and is also leading some interesting education professional development, including our School of Ice and AMS's Project Ice, and a lot of you have been to those. Keely's PhD in biology from the University of Montana studied adaptation to extreme environments and the relation to processes of evolution. So Keely's here tonight to share some Coldex opportunities with you. So welcome, Keely.
Thank you, Louise. Good evening, everyone. I think it's evening for most folks at least. And thank you to Louise and Bill both for inviting me and giving an opportunity to talk about Coldex's research experience for undergrads program. And as a way to sort of advertise in case any of you have students in your network that may be interested. So first, for those of you who may be unfamiliar, REU programs are typically NSF-funded initiatives that provide undergraduate students with hands-on research experiences, usually during an intensive summer program. And these types of programs are really crucial for engaging undergraduates in research and really developing the next generation of scientists. I am lucky to have inherited a thriving and successful REU program. And I was planning on saying that even before I knew that the previous director would be on this call. Our specific program places students within one of about 8 Coldex institutions across the United States, and over 10 weeks, these students get to work on cutting-edge research projects across various disciplines within Coldex research, some of which you've heard about today. And because of this sort of distributed nature of our REU programs, where undergrads are at different institutions, we really try to maintain a strong cohort engagement through weekly virtual meetings focused on career development and research skills, integration with local summer research communities whenever possible, structured networking opportunities with Coldex faculty, staff, and students, as well as attendance to our in-person annual meeting. So the program provides pretty comprehensive support, including a summer stipend, housing, travel funds for that Coldex annual meeting in September, and support to present their research from the summer at a major conference like AGU or GSA. And starting this year, we're enhancing the program through some mandatory mentoring training for all REU mentors, really to just further ensure that our REU students are receiving really high quality mentorship. And we hope that that really just continues to build on what we already have going to create a really welcoming and equitable research environment for our RU students. A core goal of the RU program is to broaden participation in the polar sciences, and I am proud to say that our program has successfully attracted students from diverse racial and ethnic backgrounds, gender identities, and institutional settings, including community colleges, non-R1 four-year colleges, and R1 universities. And so some of these students don't have the opportunities to engage in research at their home institutions, and this really broadens some experiences that they're able to have. Our program's effectiveness is evaluated every year by some education researchers here at OSU, and the feedback from RU alumni, some of which I'm showing here, has been overwhelmingly positive, and I think their experiences really confirm that our approach creates a meaningful opportunity for students to engage in research, to grow as scientists, particularly for students from traditionally underrepresented groups in this field. So, applications for the 2025 cohort are due on February 1st, so there's about a week and a half to submit. There is a virtual office hour session, one left on January 29th, if students have questions, and they're also welcome to email me questions as well. And this QR code will take you to the Coldex RU site. That's all from me.
Nice.
Thanks, Keely.
Thanks, Keely. And again, we'll send out this keynote PowerPoint afterwards, so you'll have all of those QR codes if you want to follow up with your students and get them involved. And I know high school students, I've sent back some of my students who graduated and were at the college level. Then I sent that along to them too, just to kind of keep them and make those opportunities available. So it's been great.
It's the question of what the age range is.
Yeah, so it's undergraduates, and that includes students who have graduated. They are also eligible for the following summer after they graduate.
From college?
Yes.
College.
All right. Did anybody we have about 3, 4, or 5 minutes for Sarah questions. Did anybody have questions for Sarah? She went through a lot. And I know when I worked with Sarah to develop some of these labs, I had a lot of questions for Sarah. She was very patient explaining things. But while we have 5 minutes here, if anybody does have any questions they want to throw out, I saw a lot of thank yous to Sarah in the chat box, but yeah, John's got a question. Yep.
Yeah, there was the last slide that Sarah had, which seemed to show a kind of a spike, I think, at the end of the for the argon data, I think it was. And I was pondering that, and then I didn't quite. Is Sarah here? Do you have your slides? If you could just like show your last slide, I just had a question about it.
Yeah, I can. Let's see.
While Sarah's pulling that up, I will tell you that we're going to show you one other lab before we wrap things up tonight, and that is the dating labs, the ice core dating labs. Those are all a result of NSF grant, and Sarah is the principal investigator behind the development of these new labs. So these are both Sarah's labs.
Yeah. Okay. So all of a sudden, there's a lot of scatter at the end. Is that just because it's these are the oldest samples, and it just seemed like all of a sudden, boom, there was a big scatter.
Here. So are you talking about? Yes, that's a great question. So this is something that we kind of have been pondering ourselves. But one thing that we do know is that so these intervals are highlighted in these different colors. And I didn't take the time, sorry, to explain what they were. But what we find is in the last roughly 800,000 years, we get an increase in the amplitude of glacial cycles. So the warmest intervals and coldest intervals, we get an increase in their amplitude. And so that might be part of the explanation that we're seeing here. It's consistent with previous reconstructions of temperature. There might be things that complicate our records, like that are kind of not applicable to these continuous ideal like ice core records, where we might have biasing of different intervals. And I don't want to get into that because one, it's complicated, and two, we're not sure. But I guess the answer that is kind of in line with our expectation is that we expect that the amplitudes of temperature should actually increase during this interval. Does that make sense?
Yes, it does. It makes a lot of sense now. I understand it.
Thanks.
Can I ask Keely too? So we only have like a week and a half or something to try and get our applications in. Maybe we'll wait till next year or what for those for the program this year. Or, I mean, how do we get? I seem to recall that there was Louise had put out the year that I was in the School of Ice, that that very same year that we had there was, I think it's the same program that you're talking about for underrepresented groups and things like that. Is this the same program? I'm not sure.
So the program has been going on for 2 or 3 years, I think. Kristen can answer more accurately, but it is, yeah.
It is the same program, Don, that we shared with your group at Dartmouth 2 years ago.
Okay, all right.
It's an NSF funded program for research for undergraduates that Coldex has taken to a big, taken on in a big way because they have such a good stable of scientists to work with as mentors with these students.
So we put in as the mentor, we put in an application and then we get students after the fact, or do we need to have students ready for that application?
The mentors are already set and they're Coldex, their faculty within Coldex. So the applications that are due in a week and a half are just for the undergraduates.
Okay, but when I meant mentor, I meant myself as an instructor. I'm going to be pulling in those students, or how does that work?
So Keely, should they still apply? Is it worth applying this year with that week and a half to go?
Students, for sure, yeah.
Don, I think what you're asking is, what would your role be if your student got chosen to be in the RET program? Okay.
That is my question.
Keely, you can correct me if I'm wrong, but I don't think you would have to do anything other than maybe recommend them. They will be mentored by a Coldex scientist. Is that correct, Keely?
Yes, that is correct. Yeah, so they'll travel to their host institution for the summer, usually June through August, roughly, and they'll be mentored by Coldex scientists and early career researchers there.
Okay, so probably at this late date, it'd be best to wait till next year. But it's the same. It's exactly the same program. Will it be available next year at the same time?
Yes, it will be offered next year as well. But as long as students are able to complete the application within the next week and a half, they're definitely.
Oh, okay, so it might be worth it. Yeah, I've got 1 or 2 students in mind that I might want to.
Yeah, I'd give them the opportunity, Don. It's a great program for their summer.
Right.
Okay. All right. Well, let me share the last few things on our agenda. New resources. Our website has been redesigned slightly. Virtual field labs are still featured prominently on there, and the new ones will post in the view all virtual field labs. But you see there is links now to the Drill Deeper video shorts. And if you click on that button on the actual icedrill-education.org website, you'll see a growing list as time goes on of those Drill Deeper video shorts just as a standalone feature. And we also have our new ice labs, and there's 2 of them in draft form that are good enough for public consumption. Those are both Sarah's labs that are out there. And embedded in those are also the Drill Deeper videos where they go in context. So moving forward as a teacher, you can look through those videos on their own, how you might use them in class, or you can download the ice labs and look at how we've contextualized those videos within the other science content that we're teaching. You notice that there are 2 labs up here. One relates to it we went through together as the extended warm-up activity, but the other one is dissolved gases and ocean temperatures. That's what Sarah talked about. And you're like, oh my gosh, how could I possibly take what Sarah talked about and put it in my students' hands if they're in high school or even entry-level college and possibly do anything that makes sense? Well, we have a lab for you. So again, it's a new ice lab. This one has just 2 explorations. One is looking at dissolved gases in a warming ocean, and the other is reconstructing ocean temperatures. Again, our goal here is to scaffold these in content-wise, so you can choose to do one or both, depending upon the level of your students. But the first exploration is really pretty simple. It's one of these you can't screw it up kind of labs. So it just has to do with Diet Coke and the solubility, and maybe you've done a demo like this or something like this in your classroom. But this is just an exercise where you take regular Diet Coke, 12-ounce bottles, and we're going to measure the water bath temperature and see how much gas stays dissolved in the Diet Coke when you put it in the different buckets of water. So the lab looks something like this. A little hole drilled in the cap. And after 5 minutes, you take the bottle out. And now the question is how much gas came out of that Diet Coke at that temperature. 102 degrees Fahrenheit, pretty warm water. Now I just want to figure out how much gas came out. So if you do that at different temperatures, you end up with data that looks something like this. And you say, wait a minute, that's really confusing data. Well, this is really what your students would get right here. At cold water, ice water bath, 60 milliliters of gas comes out. When you get a hot water bath, 300 milliliters of gas comes out. And you get that relationship that Sarah was talking about. As the oceans warm, they release these noble gases into the atmosphere. And when the oceans cool, they absorb more of the noble gases. So what are these other lines? The purple is actually cooling off the Diet Cokes before you put them in. So like if it's an ice water one, you put the Coke in ice water ahead of time. So the actual liquid is in there. And the same with room temperature and the same with warm. That's a preheated warm Diet Coke before you put it in the warm water bath. If you say, I can't mess with that, I just want to dump them in and see what happens. Well, hey, it still works. You still get that relationship. So you can just take room temperature Diet Cokes and put them in 3 different temperature water baths, and you'll still get that relationship that Sarah was talking about, and you really can't screw it up. And you notice that these 2 are parallel. When you do the lab, you might say, well, wait a minute, there's a little bit of gas already in the Diet Coke. So if you actually calibrate it really technically and figure out the total volume of the bottle and subtract out, that's that little shift there, just a systemic error that just tracks all the way through. But either way, your students can just dump the Cokes in there and get that relationship that Sarah was talking about. The that lab is up there. The second exploration really gets into a much more advanced analysis where you take known data, what Sarah showed us, that known track for 800,000 years where they calibrated that. That is this data right here. So your students can make their own calibrated global ocean temperature graph using known data from Greenland ice cores. And then here's Sarah's data from the older ice from Antarctica that they're getting 1 and 2 million years. And they can use this graph that they made to actually calibrate and calculate the average global temperature for that 1 and 2 million year old ice. So a little bit harder second exploration than the first, but hopefully all within your students' grasp, and definitely just dumping Diet Coke in hot water and watching the bubbles come out. You can't screw up there. So we encourage you to look at those. Again, the draft version is up for you to download and start to play with. If you have any comments, feel free to get back to us and let us know what you think, or if there's any suggestions that you have. And the teacher versions are being developed now. And once those teacher versions are done, they'll be up there with all these little videos and things like that for you on the back end. So with that, let me turn it back over to Louise.
Okay.
can wrap it up.
We are coming to the end of our webinar here tonight, but just want to point out that we do have a new School of Ice this summer at Dartmouth College. It's June 23rd to the 26th. So if any of you have not taken School of Ice before and you're a faculty member at a minority serving institution or an AP high school science teacher from a school with a high percentage of underserved students, please apply for School of Ice. You can email me and I can send you the link, or you can do the QR code right there. And like we said, we'll send this to you in a PowerPoint presentation, so you'll have all of those too. We hope you enjoyed tonight's webinar and that you learned something from it, found maybe a resource that you'd like to try. And we'd like to thank our speakers tonight very much. We really appreciate all of you being here and taking time out to share your expertise with us. I'd like to ask you to do an evaluation. And Bill, I think it's on the next page. Could you go to the next slide? There's a QR code there, and it's just 5 questions. And what we'd like to ask you to do is please fill this out. NSF does fund us to do a winter webinar each year, and depending on your feedback, we'll see what we create in the future for these webinars, what you'd like to see. And thank you so much for being here. And it was so much fun seeing your faces. We really appreciate it. So please take a moment.
Thank everyone for taking time out of your evening after teaching and fighting snow and ice and everything else and cold. Snowmageddon.
Please take a minute to do that questionnaire, though. They're very short questions, but they'll be very helpful to us. And when you're done, you can go. You can turn off. You can unmute your microphones and talk if you want. Ask questions or whatever while we're filling those out.
Hi, Katie.